Hello everyone, and general physics. What we're going to be looking at is our position time plot and pulling various bits of information out of one of our examples. One example here is, let's say there is a motion sensor at the origin of our graph that has position versus time in meters and seconds, and some objects starting at 4 meters forward of the position sensor starts walking backwards for 1 second until it's at the -8 meter mark, then walks forward until it's at the -2 mark, stands still for a second, then from time 3 to 4, moves forward until it's at position 8, stands still again for another second, and then starts walking backwards until the motion sensor stops at time equals 6. Well, here's how we're going to break down the information we can get from this chart. One thing that we're going to look at firstly is, of course, distance and displacement. And distance is going to be our scalar for position, whereas displacement will be the vector. Therefore, distance, we're going to need to keep track of the fact that we will not have negative signs. So when we have a chart that's all linear, for example, has different linear chunks in our plot, good rule of thumb is just to take each individual part and just find the y distance between one point to the other. And since we want to avoid negatives, let's make sure we're always having things in absolute value signs. So if we look at our first linear line chunk, essentially that goes from 0 to 1 second, we have a starting position on the y-axis of +4 and end position of -8. So the vertical distance would be -8 minus 4, -8 minus 4 meters. And then we'll leave that in absolute value signs because we want the overall distance, but we don't want it positive or negative. We just want the distance. Now we're going to add to that the next chunk, which goes from time 1 to 2 seconds. All we really care about is this line starts at -8 on the y chart, and it ends at -2. So what we're going to have is absolute value signs, -2 minus a -8, which in reality, that just becomes +8. Now we're going to add to that the next chunk, which happens to go from time 2 to 3 seconds. This one is just going to be starting at the y position of -2, ending at the y position of -2. Therefore, in absolute value signs, -2 minus -2 is actually just going to be -2 plus 2. Now we're going to add to that our next segment, which also happens to go from 3 to 4 seconds. This one, all we care about is that when this line finally stops, does not matter how much time it takes, but when it finally stops, it's ending at the +8 mark, and the line started at the -2 mark. So what we have is +8 minus a -2, which in reality will just become +2. Adding our next chunk, well, that is this line right here, which starts at the y position of +8, ends at +8. So taking the second number, we have 8 minus 8. And then lastly, what we have here is going to be from a position of 8 on the position axis. This line ends at -4. Therefore, what we're going to type in, absolute value signs, -4 minus +8, which that's all cool. Now, starting to solve this, what we're going to do now is what we're going to do now is, there we go, start basically following what's in these absolute value signs. So, -8 minus 4 that would become negative 12. Negative 2 plus 8, or negative 2 minus a negative 8, well, that's just going to be plus 6. Next part, negative 2 plus 2, that's just going to be 0. 8 plus 2, that gives us 10. 8 minus 8, that is, of course, 0. And then negative 4 minus negative 8, that is going to be negative 12. The reason why we have all these absolute value signs is because distance, in reality, is not a vector. It does not have positive or negatives. So as we're taking the linear distance from each line, the y distance anyways, we're just taking the absolute value of each. So now what this ends up being is, let's see, negative 12 is just going to become 12. Positive 6 is just 6, plus 0, plus 10, plus 0. And the absolute value of negative 12 is also just 12. And therefore, in the end, what we're left with for our distance, d, is going to therefore equal 40. And just to keep our units, 40 meters. Now, all that work was just to find out, essentially what our distance, how much did that object physically travel in our position axis throughout our graph. Displacement, that's always going to be much easier. All we care about is our final y position and our initial y position. And this can be positive or negative, therefore we're not going to have absolute value signs. So, our final y position, when our object is done moving, is at the negative 4 mark. So, typing that in, and we're going to subtract from that our initial y position, which all the way at the start of a graph, that was positive 4. So, negative 4 minus positive 4, or negative 4 minus 4, that just equals negative 8. And of course, we're going to leave that as in units of meters as well. So, what we have here is our distance, total distance traveled, 40 meters, and our total displacements. Basically, what was the net change in y position overall? Overall, the object from start to finish moved down 6 meters, or moved down 8 meters. All right, that's easy. So, next part is calculating average speed and average velocity. Both of these are very straightforward once you have distance and displacement. Reason is, average speed is just going to be our total distance divided by the amount of time we measured that distance. So, we already calculated that our total distance was 40 meters. And of course, from our graph, it only goes from 0 to 6 seconds. So that's 6 seconds in total. Now, 40 divided by 6, what that's going to end up being is 6.6, where the 6 repeats. And we're going to, of course, have that in units of meters per second. Just like since distance is a scalar and cannot be, does not have a direction, speed will not have a direction. We'll just leave it without a sign. So 6.66 repeats meters per second. Average velocity, that's easy as well, because all we need for that is our displacement divided by time. So we already calculated that our displacement was negative 8 meters, and well, we still have a total time of just 6 seconds for the entire run, so that's not going to change at all. And negative 8 divided by 6, if you wanted it as a fraction, that's negative 4. divided by 3. Or as a decimal, that would be negative 1.3, where the 3 repeats. And of course, that is still in meters per second. So unlike average speed, average velocity can be positive or negative because it is a vector. Now, the next leg of our journey is just calculating instantaneous parameters for speed and velocity. Now, unlike calculating the velocity and speed on average over the entire run, basically you would be asked to solve for velocity and speed at specific points in time. And one thing about instantaneous velocity is the slope of a position time graph at the specific point in time that's being asked. So let's look at time t equals half a second, or 0.5 seconds. Well, as we look at our chart, if essentially we look at between 0 and 1 seconds, basically the line that we're touching is this one right here. So what we need is the slope of this entire line. That's easy. We'll take our final coordinates of this line and subtract them by our initial coordinates. Just looking at the y values, we see that our final y coordinate along this line is negative 8. And we're going to subtract from that our initial y coordinate of 4. We are then going to divide that by our final time coordinate, which is 1, minus our initial y coordinate of this line, which is 0. What this is going to end up getting us is negative 8 minus 4, or negative 12, divided by 1 minus 0, which is 1. And therefore, what that really is just negative 12 meters per second. Cool. Now, basically just to emphasize, it doesn't matter that it was specifically 0.5 seconds. You could have been asked, find the instantaneous velocity at time t equals 0.77 seconds, so somewhere around here. That would still touch this line right here. So your calculation would still be the same. Now let's look at 1.5 seconds. Well, 1.5 seconds, that touches this line of our graph. So that goes from this point to this point. Taking our y values, that is going to be negative 2 minus negative 8, which just becomes plus 8. And then we'll divide that by 2 minus 1. Now, negative 2 plus 8, that would be 6. 6, 2 minus 1, that would just become 1. So what we're left with is positive 6 meters per second. I have a positive sign just because velocity is a vector. So if it's positive, it's okay to put the plus sign in there to indicate that that's the direction, just so that's not confused with a missing negative sign. Looking at the instantaneous velocity at time 2.5 seconds, well, if we look at our graph on the time axis, 2.5, we're actually touching this linear line right here. So to calculate the slope, we have a y value of negative 2, a y value of negative 2. So negative 2 minus negative 2 just becomes negative 2 plus 2. And then dividing by our time, or our x coordinates, that is 3 seconds minus 2 seconds. So negative 2 plus 2 is 0. 3 minus 2 is 1. So that just becomes 0 meters per second. And for 0, if it's a vector, you don't need to put a plus or minus sign. So looking at 3.5 seconds, well, if we look at 3.5 seconds, our graph, the dashed line, is this part right here. So we're actually on this line. So calculating the slope of this particular line segment, our final y-coordinate would be +8. And we're going to subtract from that our initial y-coordinate of -2. Minus a -2 just becomes +2. And as far as our time difference, well, this point correlates to 4 seconds, and this point correlates to 3 seconds. So 8 plus 2 would be 10. 4 minus 3 is 1. 10 divided by 1 is just 10, or +10 meters per second. Our next one is going to be at 4.5 seconds. So if we're somewhere between 4 and 5 seconds, we're touching this line right here. Again, that time, that could have been 4.2 seconds. We would still end up touching the same line segment. Could have been 4.9. We would still be touching this line segment. So all we care about is just measuring this line segment right here. So what that's going to be is our final y-coordinate of +8 minus our initial y-coordinate of +8. And then we'll divide that by our x-coordinates, which the final one is 5, minus the initial one of 4 seconds. So 8 minus 8 is 0, 5 minus 4 is 1, 0 divided by 1 is just 0, of course, 0 meters per second. And then the last one that's being asked for, time at 5.5 seconds, what's the instantaneous velocity? In other words, what's the slope of our position time plots at that point in time? Well, going on our x-axis, at time 5.5 seconds, what we're really dealing with is this line segment right here. So the slope of that is going to be, of course, our y-coordinate -4 minus our y-coordinate of 8 divided by our x-coordinate of 6 seconds minus our x-coordinate of 5 seconds. -4 minus -8, that would be -12, divided by 1. That is going to, of course, be -12 meters per second. So, cool. That would be the instantaneous velocities at those points in time. This particular example was pretty straightforward because the numerator, or I should say the denominator, always ended up equaling 1. But you're going to have examples where these line segments go across more than 1 second. So just watch out for where the start of a line segment is and the end of it is. The reason why we calculate our instantaneous velocity first is because instantaneous speed is very easy once you have your instantaneous velocity. It's essentially the absolute value of the instantaneous velocity. So at time 0.5 seconds, if the instantaneous velocity was -12, well then the instantaneous speed is going to be just 12 meters per second. Essentially, we removed the negative sign because speed as a scalar does not have a direction, positive or negative. Now then, at time 1.5 seconds, if the instantaneous velocity was +6, then that means that this instantaneous speed is going to be 6 meters per second. At time 2.5 seconds, with an instantaneous velocity of 0, our speed is also going to be 0 meters per second. For our time 3.5 seconds, our instantaneous velocity was +10. Therefore, our instantaneous speed will just be 10 meters per second. For time 4.5 seconds, we again had an instantaneous velocity of 0, which just gets us to an instantaneous speed of 0 meters per second. And finally, with an instantaneous velocity of negative 12 meters per second, at time 5.5 seconds, the instantaneous speed would just be 12 meters per second. So effectively removing that positive or negative direction sign as we went from instantaneous velocity to instantaneous speed. Now, one last thing you might be asked, going from a position versus time plot to a velocity time plot, or if you start with a velocity time plot, you can do the same thing to draw an acceleration time plot. What we're going to do is take our instantaneous slope values and just draw them as a graph. So if you're asked to take from position versus time to draw the velocity versus time plot, that's pretty easy. V of t in meters per second versus time t in units of seconds. Basically, going from our prior graph, we saw that the instantaneous velocities we calculated, the lowest they ever got was negative 12, the highest they ever got was positive 10. So let's just do a chart where the velocity axis goes from positive to negative 12. Now, what we're now going to do is our time axis from 0 to 6 seconds. What we're going to need to know now is be very careful as you draw these. Because our position versus time plot was linear, we are going to have straight, flat lines across our velocity versus time plot. Now, what we measured from 0 to 1 second, the slope was negative 12. Therefore, between 0 and 1 second, fill in a horizontal line that has a value of negative 12. Do not fill in a specific point, but a whole line. From 1 to 2 seconds, we found out that the slope was positive 6, which is why we have a line here for the entire time range of 1 to 6 seconds. It equals positive 6 on the velocity axis. From time 2 to 3 seconds, we found out that we had a 0 slope for our instantaneous velocity. So that's why I'm just highlighting that part here to distinguish it from the axis. From 3 to 4 seconds, we calculated that we had a slope of positive 10. So that's why between 3 and 4 seconds, we're filling in this line that correlates to positive 10 on our y-axis. From 4 to 5 seconds, we have a slope of 0. And from 5 to 6 seconds, we had a slope of negative 12 again. And then I just had little dashed lines to connect the end of one point on our velocity graph to the start of the next chunk. Be careful as you do this on future problems. We will not always have a graph where each line segment is only 1 second long. So make sure that as you draw that in your velocity versus time plot, you might have some line segments that span 2 seconds, 3 whole seconds, 1 second. Just be careful as you're converting position versus time information to velocity versus time information. Now then, that finishes that little video on this concept. Now, as always, if you want to see the like button or the subscribe button glow, hopefully that starts working now just by saying it. Whatever the case though, hope you guys got value out of this video, and as always, peace.